Let's take a look at a theorem here. If f is a function of three variables that has continuous second order, the second order is important here, this continuous second order partial derivatives, then the curl of the gradient of f is equal to the zero vector. And actually, that's pretty easy to prove simply by generically figuring it out. So what is the curl of the gradient vector, or the gradient? Well, that's going to equal this del operator cross the gradient. And I'm going to set that up obviously as a determinant. So I have I, j, and k. And then I have this del operator, the partial with respect to x, the partial with respect to y, the partial with respect to z. Then, of course, the gradient is going to be the partial of f with respect to x, in component form, obviously, the partial of f with respect to y, and the partial of f with respect to z. So now all I really need to do is go ahead and work out this determinant. And that's going to give me the partial with respect to y, partial of f with respect to z. So that's going to give me the second partial of f. And then the partial with respect to y, partial with respect to z, minus, again, I'm going to have the second partial of f with respect to y, and then, respect to z. So give me I. See, minus, I'm just going to work out the determinant. I'm not going to worry about the fact that the curl actually has a plus here, because I'm going to factor out a negative. I'm just going to leave it as is right now. See, j was give me the partial of x. So that's going to be the second partial of f with respect to x, then z, minus the second partial of f with respect to, well, x, and then z. That's k. Plus, this last one is going to give me the second partial of f with respect to x, then z, minus, again, I'm going to have this second partial of f with respect to x, then z. Oops, that should have been a j, sorry, and k. Now, obviously, these are equal to each other, so this is 0. These are exactly the same. That's 0. These differ? No, they're not. They're actually exactly the same thing. So obviously that is 0. So this is actually going to be equal to 0i plus 0j plus 0k, which is the definition of the zero vector. Now, recall that a conservative vector field is a vector field such that we can write the vector field as being equal to the gradient of some function of f. So with this idea, we can actually just rephrase this last theorem, and we can rephrase it as simply say that if f is a conservative vector field, then the curl of f is going to be equal to 0. Now, this tells us how to determine if a vector field is not conservative, but it does not tell us how to determine if a vector field is conservative. That's because this is a one-way implication. If f is conservative, then the curl of f equals 0. This is a one-way implication. I can't come back and make the implication in this direction, at least not yet. We don't have, or we're missing a kind of important piece here to allow me to go back in this direction. So right now, if I have a vector field and I find the curl of that vector field, and that curl is not equal to 0, then that tells me that that vector field is not conservative. If I find the curl of f and it is 0, the vector field may or may not be conservative. So right now, all I have is the ability to go in this one direction. So to just kind of repeat that, if the curl of f equals 0, then f might be conservative. However, if the curl of f is non-zero, then I know that f is not conservative. Let's take a look at a quick example here. Let's just consider the vector field e to the x, e to the xy, e to the x, y, z. So what I want to do is find the curl to this. I'm trying to figure out whether this thing is conservative or not. So what I need is the partial of r with respect to y minus the partial of q with respect to z, I. That's the first component, so let's just start there. The partial of r, this is r, with respect to y is going to be x z e to the x y z minus the partial of q with respect to z. This is q. So this is 0. I'm done. This is not going to be 0. It doesn't matter what happens beyond here. The I component is going to be xz e to the xyz. That's clearly non-zero. Therefore, I know that f is not conservative. Okay, if this had turned out to be 0, if I finish it up and I found that it is 0, then I could go to the idea that it might be conservative. I don't know if it is or not, but it might be. But seeing it was non-zero, then I definitely know it is not conservative.